So now I'm going to go over the exception to the octet rule. The first exception that I'm going to go over, actually this video is going to be about the exception which is less than an octet of valence electrons available. So as we know, we have to, based on the octet rule, each of the electrons has to be able to share or have total of 8 electrons around itself, whether they're their own electrons or they're shared electrons. So there are some exceptions, and one of the exceptions is less than an octet of valence electrons. And usually this type of situation happens with compounds of boron and beryllium. So we're going to go over a very common one, which is boron trifluoride, and it's this boron trifluoride. Okay. So let's try to make the Lewis structure diagram from scratch on this one, and then we'll look at we'll look at the exceptions. So boron is in the middle since it's a single atom, and then we've got 3 fluorides. So fluorides I'll just put around boron, kind of like this. Okay, now we got to figure out how many total electrons we're going to have. So boron belongs to 3A group. So boron will have total of 3 valence electrons available. Fluoride belongs to 7A group and is going to have 7 electrons available. Since we've got 3 fluorides, we're going to have total of 7 multiplied by 3, a total of 21 electrons available from fluoride. So if you add the valence electrons for boron and fluoride, we have total of 24 electrons available. So now let's just put our electrons where they belong for now. So boron has 3 available, so I'm just going to put 3 electrons around it. And then fluoride, each of the fluorides has, let me change the color so this way it's a little bit easier to see. Let's get green. So fluoride has 7 are available for fluoride. So let's just do, I'm doing 2, 2, 2, 2, and 1. So I'm gonna go ahead and do it around each one of them. If we have to change them around, we can erase and start all over. So I've got total of 7 for fluoride and 3 for boron, so I think we got it handled. So now let's do some connections. If we connect fluoride and boron like this, we're gonna then complete the octet rule for fluoride, since we're gonna have 6 here and 2 of this edge. So this is completed, and also this one we can do the same thing. Then fluoride will be completed. And if we did the same exact thing over here, this fluoride will be satisfied. So we only have left is boron, which is not satisfied because boron has 3 of its own, and the other 3 that are given to it by that are shared with it by fluoride. So we have only 6. So that's not quite working for boron as far as the octet rule. So we'll have to figure out a way to reposition the electrons to satisfy the octet rule in this case. So let me have one of the fluorides give its electron to boron, give its one of the electrons to boron, and I'm going to reposition another electron. So in this case, I'm repositioning one that I just erased over here, and then I'm giving one to boron. And then I'm going to go ahead and make a bond over here. So looks like this one is still satisfying the octet rule for fluoride. The other ones we left by the way they are, and the boron's octet rule is satisfied as well. So based on the octet rule, this structure looks very good because each of the atoms has, whether they're shared or not, total of 8 electrons. So, but before we complete this problem, we need to look at the formal charge on each of the atoms, okay? Because formal charge is important. If the formal charge is incorrect, that means that it's not a very stable, or it's not the right correct structure for it. So in this case, fluoride, for formal charge in fluoride, we've got 7 for the neutral. Let's count how much it's got now for, in this case, 1, 2, 3, 4, 5, 6. So it only has 6 on its own here. So it has, so the charge for neutral is 7 for this one, but it only has 6 right now. So if you subtract the 6, we got 1 that's left over, and it's actually positive 1. So charge on this one is plus 1. This one looks like it's fine because we've got total of 7 electrons that are belonging to fluoride. 1, 2, 3, 4, 5, 6, 7. So the charge, so if you say for this one, 7 minus 7, you get 0. So the formal charge for this guy is here, 0. So this one is pretty much replica of that. Again, it's got 6 that are lone electrons, and then we got 7th that is connected to borons. So basically the same thing here, 7 minus 7, we get 0. So the formal charge here is 0. Now let's look at the formal charge of boron. So boron has its own neutral atom. Valence electrons are 3. So we need to subtract how many electrons it's got on its own right now. 1, 2, 3, 4. So it actually has 4. So if we subtract 4, we get -1 charge. So boron actually has minus -1 charge here. So now let's look at the electronegativity rule. The electronegativity goes up, so electronegativity goes up as we move across the period, okay? Electronegativity. Okay, as you see, it's going up. So technically, fluoride that's over here has to be more electronegative than boron. But as you can see in this case, it's the opposite. Fluoride is the one that's got positive charge, and boron is the one that's got negative charge. So this structure is not very favorable structure because it does not follow the electronegativity rule. So therefore, we're going to try to somehow adjust it so that we're going to have to break the octet rule. So we're going to have to break the octet rule, but we're going to try to make sure that we follow the electronegativity rule by breaking the octet rule. So how about if we give fluoride its 0 formal charge again? We're going to go ahead and remove this bond right here. So it's got 2 electrons. So now we've put the electrons back the way they were. So we've got 7 electrons here that belong to fluoride. So now the formal charge is actually 7 minus 7 is 0. So in this case, the formal charge in fluoride is 0. Now this one we haven't changed anything at all, so it's still staying at 7, which is formal charge 0 over here. And this one we haven't done anything at all either, so 7 minus 7 is 0. So as far as boron is concerned, this formal charge is actually going to turn to 0 as well because we removed the double bond that was here, so we're only left with 3 electrons that belong to boron. 1, 2, 3. So we're going to have 3 minus 3, which equals to 0. So now the formal charge in boron is 0 instead of -1. So this is a more stable structure, or a dominant structure, and that's the structure we're going to stick with, even though, as you can see, boron in this case does not follow the octet rule. By But this is a proper structure based on the electronegativity rule, because we're not violating the electronegativity rule like we did in the earlier structure, because we have zero formal charge for boron as well as zero formal charges for the three fluorides.